everyone, in this lecture we are going to discuss the concept of hybridization. So hybridization is important for various elements, but in the case of carbon, this is basically responsible for all the properties of carbon materials, right? And also when we talk about properties, then the application areas are very strongly connected to the properties, right? And we also have the manufacturability that is connected to the properties, because manufacturability is strongly influenced by the crystal structure of carbon. And why do we have different crystal structures of the same element? Well, that is all because of the hybridization at atomic level. So what is hybridization? When two atoms come together, they have some sort of merging of their energy levels. That is what we call hybridization, or these energy levels are called hybrid energy levels, where the electrons are redistributed. Okay, we will get into that. Before we talk about what are orbitals. Okay, so in the previous lecture I told you a few things about the electronic configuration of carbon. We also discussed different isotopes of carbon. You now know that C13, C14 also have their own application areas. Now what we are talking about is the bulk carbon material. Bulk carbon these are the materials that are available to us for manufacturing purposes. Okay, so they mainly contain carbon-12. They may have some C13, C14 as well, but we don't worry about that for now. What we need to understand is now how carbon behaves at an electronic level. So we don't think about the nucleus anymore. Okay, you must have learnt about orbitals. You also probably know a few fundamental things about the idea of hybridization as well. Okay, when you learn about an atom or atomic structure at school level, basically what you learn is there is some sort of nucleus, which is correct. So you have a nucleus which contains protons and neutrons and other nucleons, and then around that nucleus, what you have is you have electrons that are circling, that are orbiting in a certain, let's say, circular path. This is the Niels Bohr model that most of us learn at the school level. Okay, the model has a lot of advantages. It's also a very convenient model for explaining the atomic structure, and it actually does justify a lot of chemical properties of the materials. However, the idea that electrons are taking a certain path, they are orbiting around the nucleus, that is incorrect. Okay, why is it incorrect? Because orbitals are basically, they are not any given path. They are basically nothing but probability density functions. What does that mean? That means that there is a certain region in space where you have the highest probability of finding an electron. Okay, we do not know anything about the path that the electron takes. So let us take the example of an s orbital. You know that orbitals are subshells. I have also written here, you know what are 4 quantum numbers. We know that the principal quantum number will define a shell, and within this shell then you have certain subshells. So these are other smaller energy levels, discrete energy levels, where you can find the electron. These discrete energy levels are what we call the electrons, and that is what I'm saying is the region in space where you have the probability of finding the electron. Okay, now let's take the example of s orbital. So we have a spherical shape of this function. Okay, what does this mean? At any given point, if I try to find my electron, then I will find it within that sphere. Okay, so I'll find it here, after some time here, and then here, and then here, and then here, and then here, and there. So on. If I do this infinite number of times, and every time I find the electron, I mark a point there. In that case, all those points will be confined within that sphere. Okay. Now this also will, you might have a higher probability density closer to the core of that sphere, and towards as we go far from the nucleus, then we also have lower probability or smaller probability. However, the area where we will find, this is the confined region where we will find the electron. Okay, so that is what we call as the orbital. Now, as I said, that we don't know anything about the path of the electron. So when I was saying that we find the electron here and then after some time here, I don't know how my electron went from one place to another place. I don't know if it took a circular path. I don't know if it, where did it go? I really don't know anything about the path of the electron. So this is something that you need to keep in mind. Okay, that is number one. Number two, electrons are indistinguishable from each other. Indistinguishable means if I have, let's say, 5 electrons in a certain system, I never can say accurately that this is that electron and this is that electron. The electrons might be exchanging places, we don't know. We cannot tell one electron from another. So we cannot differentiate between two electrons. This does not mean that we don't have 5 electrons. We do have 5 electrons, and they are 5 different electrons. But we can never say for sure that the electron that I find in this place was that electron. Okay, so they are indistinguishable from each other. Okay, fine. Now, how do we find out these shapes of the electrons, orbitals? So I told you that s orbital is spherical. You also know that when we talk about p orbital, we have this dumbbell kind of shape. And also in that dumbbell, there is a node. Node is the place where you have the 0 probability of finding an electron, or almost 0 probability. So how did I come to know these shapes? Okay, there are certain experimental methods. There are certain also simulations that you can perform, and you can kind of guess the probabilities of finding the electron in a certain region. But fundamentally, the shapes of the electrons are derived from an equation known as the Schrodinger equation. Okay, so Schrodinger equation is something. The idea of Schrodinger equation is not something that I'm going to cover in this course. I will be providing you with some of the other NPTEL lectures where you can learn it, and of course there are many other resources also from where you can understand the quantum mechanical aspects and how do we solve the Schrodinger equation. Here I have mentioned a very general form of this equation. So you can also have time dependent equations. This is just the very general time independent Schrodinger equation that I have written here. H psi equals E psi. So now I'm going to describe the what is the meaning of different terms here. H is the Hamiltonian operator. Okay, so what is an operator and what does it indicate? Okay, so for any, let's say in classical mechanics, if you have a particle, how do you define the energy, the overall energy of that particle? You will say that will be the summation of the kinetic energy and the potential energy. And then you will have some variables, and that is what you will solve for a given particle in classical mechanics. In the case of quantum mechanics, we have what is known as the operators. And these operators, so in this particular case, the Hamiltonian is an operator which is equivalent to the what you in classical mechanics you will have for kinetic plus potential energy. However, this operator then operates on a certain function, which in this case is the wave function. So if it is a time independent Schrodinger equation, in that case Hamiltonian operator will give you some values which are the values of energy. And these values are basically the orbitals. So these are basically nothing but orbitals are nothing but discrete levels of energy. So this is something you need to understand, that orbital is not a physical thing. It is not a given path. It is not even something that we can. It's just a level of energy. That is where we have the highest probability of finding our electron. So E here, the other one more term that is left is E, which is the eigenvalue. Eigenvalue is basically the most probable or most likely value of something. So eigenvalue of energy will give you basically the shapes of the orbitals. So this is how we find out the shapes of the orbitals. One more important thing that you need to understand is that we are always solving the Schrodinger equation only for hydrogen atom. Hydrogen atom has 1 electron, so we are only solving it for 1 electron systems and not for multi-electron systems. So all these shapes are derived by solving the time-independent Schrodinger equation for hydrogen system. Okay, fine. So yeah, here I have written we do not consider the the interaction between multiple electrons. In fact, that is the reason we are solving it for a single electron system. Okay. One more interesting and important thing for you to understand is that these are Orbitals are discrete probability functions. When I say discrete, that means in one orbital, the probability of finding, the overall probability of finding an electron will be 1. The integral. Also in another orbital, the integral will be 1. In a third orbital also. So these are, individual discrete probability density functions. Okay. Now, what do I call a free electron? And this is why when we talk about hybridization, it's important for you to understand that the orbitals are not really paths, and this is just a probability distribution. What is a free electron? Free electron is the electron which has zero probability of being found in any of the orbitals that participate in bonding. So if there is an orbital which is not participating in bonding, which means there is a certain energy level which is available for the electron. The electron can most likely be present there, but it will not participate in bonding. And hybridization, which we will come to in the next slide, that only takes place at the time of bonding, or between the electrons which are participating in bonding. So if there is, let's say, some unhybridized orbital in your system, in that case, the electron that stays only in that unhybridized orbital and it has zero probability of being found in any of the hybrid orbitals, that electron will be called the free electron. Okay, fine. Now you must have seen these kind of diagrams. So if I draw p orbital, I will also draw it like that perhaps in this particular course, again because this is just an easy representation, making two lobes. However, please note that these lobes, they kind of look like this. Okay, so these are just, as I said, if I perform any experiment and I make a mark, I make a dot every time I find the electron, then ultimately if I do this, a large number of times, in that case, this is the kind of image I'll get, and that is what the orbital would look like. But for easy explanation purposes, even I will be using these kind of drawings. Okay, so now let us talk about the hybridization specific to carbon. So how many atoms, how many electrons do we have in a carbon atom? You know that we have altogether 6 electrons, but 2 of them are in the 1s shell, so they are not in the valence shell. We don't really at this point talk about them. We only talk about the 4 electrons which are in the valence or the outermost shell. Okay, in this outermost shell, the n or the principal quantum number equals 2. Okay, and then there are 2 subshells, 1s and we have s type of orbitals and we have p type of orbitals. Okay, so the azimuthal quantum number, or L, you probably already know, this is 0 for s and this is 1 for p orbitals. Okay, so the allowed values of ml for the p orbitals is 3, -1, 0 and +1. So we can have 3 types of p orbitals: px, py and pz. This is how we call them. Okay, so altogether how many electrons you can fill? You can fill 6 electrons. These 6 electrons can also come from another atom. Okay, so this is what we have for carbon. Now what happens at the time of bonding? Let's say I have the carbon atom and another carbon atom comes close to it, or another heteroatom, let's say hydrogen atom, comes close to it. At the time of bonding, the s and p orbital of a given carbon atom merge their energy levels and form what is known as the hybrid energy level. And these hybrid energy levels are what we call hybrid orbitals. Okay, so now we have the molecular orbitals formed with hybrid energy levels, and these energy levels are slightly lower than the energy level of the p orbital. So I'm going to describe that with this diagram. Okay, what do you see here? So E is the energy. Okay, in the case of ground state carbon atom, you have this 2s and 2p orbital. So there is a slight difference between the energy levels of s and p orbital, of course. Now when it is excited, excited state means this is the state when your carbon atom will have only when there is a possibility of bonding. So in the excited state, what happens is this one electron which was in the ground state, you see that 2s orbital had 2 electrons, and the 2p orbital also had one unpaired and one unpaired electron. Okay, but the third pz type of orbital was there was no electron available there. Okay, now in the excited state, one electron, because again the difference of the energy of these two level 2 orbitals is not that high, so in the excited state, one electron from the from 1s 2s orbital goes into the 2pz orbital. Okay, so this is about the ground and excited state. Now what happens during hybridization? Now these 4 unpaired electrons, the orbitals with 4 unpaired electrons, they form a certain hybrid energy level, which is the hybrid orbital you can see in the middle. In the case of sp, you have one s and one p orbital which go into this hybrid energy level. In the case of sp2, you have one s and two p orbitals which will form the hybrid orbital, and in the case of sp3, all 4 will participate. So 1s and the 3p orbital, all of them will form these 4 molecular orbitals which have a slightly lower energy than the p orbital that we have in the beginning. Okay, so this is basically the idea of hybridization. Again, this might be something that you already understand, but it is important because you will see in the next couple of lectures that the shapes of these hybridized structures or molecular orbitals, or the after bonding whatever is formed, the shapes at atomic or molecular levels are basically what will define the crystal structure at a larger level, at a larger scale. And also, of course, the sp2 type of carbon materials, which are very, very interesting for us. So from here, you should already see that there is one unhybridized p orbital. And this unhybridized orbital is what is responsible for all the interesting properties of graphite-like carbon materials, even including graphene, which is the single layer of graphite. All the interesting properties are because of this unhybridized p orbital. In the case of sp hybridization, you will see that there are 2 unhybridized p orbitals, so we should have even many more interesting properties. Well, sp hybridization is more common in the case of compounds rather than elemental carbon. Although there is one certain form of elemental carbon which has sp type of hybridization. This is something we are going to discuss in the next couple of lectures. Okay, now we are coming back to when we have the hybrid orbitals, how do we fill the electrons? Again, there are all of your standard rules. For example, Pauli's exclusion principle or Hund's rule. All of these remain valid. And then once we have the hybrid orbitals, we fill the electrons in the normal standard using the normal standard rules. Okay. Importantly, the number of atomic orbitals will be equal to the number of molecular orbitals. So you cannot have, just by using 1s and 2p, you cannot have 5 or 6 hybrid orbitals. Okay. So here I have only shown the 3 primary hybridization states of carbon atoms. Why do I say primary? Well, these are the only 3 possibilities. If you think of it in the sense that if you think that orbital has to be an integer, because as I mentioned, the overall probability of finding an electron in the orbital will be 1. So you will, as such, the orbital should be an integer, right? It cannot be a fraction. However, the probability of finding the electron inside an orbital can be a fraction, because probabilities can very well be, fractions. Okay. This is something that is very important for you to understand, because what we are also going to learn in the next few lectures is that there is a possibility in the case of carbon of finding certain geometries which would only be possible if the hybridization state was between sp2 and sp3, or in some cases between sp and sp2. What I'm saying is, if you have certain geometry which is in between sp2 and sp3, then you have if you back calculate the hybridization from there, then you will get something like sp2 plus n. And this is something also that is very important for us, and we are going to learn in this course. This is extremely important important when it comes to manufacturability of carbon, because you often find these kind of structures in your, at least in the large scale carbon materials, which are neither graphite-like nor diamond-like, but they are somewhere in between. And also, then it becomes very difficult to understand them. These are the kind of structures which lead to the disorder in carbon, and that is the reason we don't call carbon completely amorphous, because we will find some sort of crystallinity at all points. So it is for us very important to understand that although the orbital itself is a well-defined energy level, so you can think of it in terms of an integer, but the probability of finding an electron doesn't need to be an integer, because probability can be a fraction. Okay, so now I already mentioned that these kind of images, these are just for easy representation. So I'm using these kind of images also just to tell you that you have, this is the shape of your s orbital, and then you have 2px and 2py and z. These kind of lobes can be found in these orbitals. And then when we have the hybridized orbitals, then also we have certain shapes, and these shapes basically will ultimately define your large scale crystal structure. So again, I'm using these kind of diagrams. So once you have the hybridized, this is the sp3 type hybridization I'm showing you first. Then what happens when these energy levels merge? The new hybrid energy levels that are formed, they have the probability distributions in such a way that you get this kind of a a tetrahedral kind of structure. This is what is known as a tetrahedral structure. Okay. Again, so there are certain regions where now you see that the lobes have, some lobes have a higher probability and the other lobe has become smaller. This is, again, there is no change in the physical shape or anything like that. These are just the possibilities. These are the probability distributions. So now there is a higher probability that you will find electrons away from each other, because you see, when you have the electrons, then they are always trying to move away from each other after bonding. So now when you have two sp3 type carbon atoms, they bond together. So 4 atoms of 4 electrons of one atom and 4 electrons of the second atom, they go into these 4 molecular orbitals, which are your hybrid orbitals. Okay. Now all of these electrons, they want to move apart from each other. They want to go as far as possible from each other, and in that case, this particular geometry is the most suitable geometry for them. Okay, so another slightly different representation would look like this. These are the sp3 hybridized orbitals. So often you will hear that either the word tetrahedral or pyramid shape. So if you connect this, all of these electrons, let's say if the electrons are sitting at the end, at any given point, end of these, the lobes that I have shown, then in that case, if you connect them, then what you will get is this pyramid-like geometry. So this is the geometry of diamond type carbon. Also, by the way, here I have only shown one hybrid orbital, one set of hybrid orbital, but this only happens at the time of bonding, which basically means that you will have another one like this. And here I have only shown the 4 electrons, and the 4 electrons of another similar hybridized orbital will then complete the octet, and all the electrons will get paired up and there will be bonding. All of these bonds will then be sigma type of bonds. And that is why diamond has a very, very strong geometry, and it also has very strong bonding and no free electron available for electrical conductivity or anything. And then at a larger scale, also the diamond crystal structure has these pyramid-like shapes, and that is why when we cut the diamond, we get these different facets. Okay, so these are like the facets of a pyramid. Okay, so this is how your sp3 type hybridized orbital look. What happens in the case of sp2? Now you have, as you can see here, you have one s orbital and 2 p orbitals. The third one is unhybridized. It does not participate in hybridization. Okay, fine. In that case, you have this kind of shape. Now, for three hybrid orbitals, if they want to move as far from each other as possible, the optimum geometry is a planar geometry. So you have a plane triangle, and all three corners will, again for an easy representation, will contain the electron. The electrons can now move as far from each other as possible. Again, if I take one such sp2 hybrid orbital, then it will look like this. Basically, these kind of geometries are known as trigonal planar geometries. Now, I have not shown the unhybridized orbital here. Okay. What happens in the case of sp2? So now, sp hybridization, you only have one s and one p. Okay. Now, one s and one p basically will give you something like a linear type of shape. So again, because there is only one such orbital shown here, then you see only half of this shape. Another half will be completed by another neighboring atom, and what you will have is a linear type of final geometry of the molecule. Okay, so these are the three different types or different shapes of hybridized carbon atoms, and this is what is ultimately defining all of the properties of carbon materials at a larger scale. So this is the geometry which I have shown. This basically tells you this is how ultimately the molecule will look like. Okay. Yes. So now, if you can think about it, we are going to discuss this after one or two lectures. These are the shapes of the sp2, sp3, sp hybridized orbitals. But if I give you some random number, as I mentioned previously, let's say sp2.2, can you think of what is the geometry? What will it look like? Okay, sp2.2 means it should be between diamond and graphite. But between diamond and graphite, think of a geometry that your hybridized orbitals can adopt.